All right, Strange Loop. It's a pleasure to be here with you today. My name is Rob Dickinson. I work at Intel, and I'm here to talk to you about persistent memory. I've been working on. I'm a software person, and I've been working on persistent memory technology, not from the hardware side, but from the software side. How do we take existing software and use this? How do we write new software to use this stuff? And it's been really interesting. We've certainly found some things that work, and we've certainly found some things that we wouldn't recommend. And so that's kind of the point of this talk today. Oh, anybody here looked at persistent memory before? Heard about persistent memory? Wow, a lot of hands. Great. This will be a good talk. So as I said, I'm a software person. I'm a database person. And this is a fairly short talk that we're going to have here today. So I wanted to throw out my contact information. If you have any questions after this, we may not have time to get to a lot of questions, but happy to talk to you after this. And as you can see, I'm wearing my Intel shirt here, and so we're not a sponsor here, but if you want to grab me as I'm walking around the rest of the show too, I'm easy to find, so please stop me and ask me any questions after this as well. So life of a software person at Intel is pretty much life as a software person anywhere. We're out to build cool stuff. The fun part about it, though, is that we get early access to real hardware. We get early access to samples and preview hardware. And then there's a big emphasis at Intel on going out in the community and sharing our results. We don't tend to sell our code. We're a hardware company. So we like to go out and share best practices, forums like this. We're also big contributors to open source, both Linux kernel and our own projects. So I'm not one of these crazy people in the bunny suit. This is actually a real Intel employee that, for some inadequately explained reason, decided to do an ultra marathon in his clean room suit. I guess he didn't get enough time in the clean room suit at work, I guess. I don't know. They're a different breed. We are going to talk about hardware today. We're going to talk about CPUs and CPU caches and memory and storage and a few other things, but we're going to keep this pretty high level, really looking at this from the software side. What's the impact to us as programmers and people trying to deliver systems for this technology? So we're not going to go down into the deep, low-level details about how this media is built and how it's fabricated and all the magic things they do in the garage to make that happen. The other thing I wanted to mention is a lot of what we're going to talk about today is not really Intel specific. Non-volatile memory, storage class memory, or persistent memory, whatever moniker that's being sold under, a lot of these technologies are very similar. And in fact, most if not all of the programming and kind of systems design things that we're going to talk about today apply equally to any of these kinds of memory. So not just Intel specific, but if you're using NVDIMMs from HP or Samsung, for example, a lot of these things are going to apply. So what is persistent memory? Thankfully, a lot of people here put their hands up, so we don't have to do too much background. But for those who don't, it's the stuff on the right. It's not the stuff on the left. Intel's not really getting into banana-based storage, but this is just kind of a funny picture that we like to use to show this stuff. This really is the future. I really feel like this is the future. If you think about when you first learned programming, you probably learned some machine code, and your programming model was, I'm just working with registers, or I'm just working with memory addresses. This is kind of getting almost all the way back to that. What if you didn't have to page data in and out? What if you didn't have all these spinning disks or SSDs out living on a bus somewhere? What if it was just your CPU, your code, and your memory? It's kind of a neat way to think about it. Intel's specific offering around persistent memory is what we call 3D crosspoint technology, and that's illustrated by the picture on the right. As I said, I'm not the guy in the bunny suit, so we're not going to get into the physics of how this stuff is built, but it really is amazing. If you are a materials person or a semiconductor person, this is really a fascinating topic on which I am not qualified to speak. As the name suggests, the biggest feature of this memory is that it's persistent. And what we mean by persistent is that it holds its contents across a power cycle or when the power is off. And obviously that's a big difference from dynamic memory, which constantly has to be refreshed even while the system is running. It forgets its data so quickly. This is large capacity memory. It's 3 terabytes per socket in the initial generation, so 6 terabytes for a 2-socket system. And pricing has not been announced yet for the DIMM factor version of this, but the general guideline that we're giving is that it's cheaper than DRAM. So that's the price point that we're trying to hit. This persistent memory revolution is already here. We're already using this 3D crosspoint technology in our Optane SSDs. These are already shipping now. And the DIMM form factor, which is the banana, wait, not the banana, the other one, that will be shipping next year, so in our next generation platforms next year. So the biggest point that I want to try to get across today is that even though we're calling this memory, persistent memory is not memory. It's not DRAM. And it's not storage. It's not SSD either. It is very tempting when you first come into thinking about persistent memory, it's very tempting to want to equate persistent memory exactly to being DRAM or exactly to being storage. In fact, I've read a number of articles over the last year where people said something like, you know, once this persistent memory comes out, yeah, it may take a year or so for it to really ramp up into production, for everybody to be switched over for it. But then that's all that we'll use. That's all that we'll have inside our computers will be persistent memory. And as somebody selling persistent memory, that certainly sounds great, but it's not very realistic. The fact of the matter is, all of these technologies have different operating characteristics, they have different cost characteristics, and they have different wear characteristics. And all of these things go to persistent memory really emerging as a new tier of memory. So it's completely logical, and I couldn't help but thinking like this for a while, even though people were telling me not to. It's really comfortable to try to equate this directly to, oh, I used to do this in DRAM, now I'll just do it in persistent memory instead. Or I used to do this in SSD, and I'll just use my persistent memory like an SSD. That's certainly comfortable from a thought model perspective, but when you really start to dig into the details, you start to see the differences between these. So in terms of capacity, persistent memory is in the terabytes of capacity. Obviously, there's choices here around what sizes of DIMMs you use and also how many DIMMs you use, what ratio you use between regular DRAM DIMMs and persistent memory DIMMs. That's up to you, and that's also up to the platform OEMs to set the bounds on that. Power safe durability, we already talked about. The access model of the media is one of the most important ways in which these are different. So our SSDs that we know and love, in fact, all of our storage technologies pretty much are all block-based, and the blocks are usually 4K. On memory, on the other side here, memory is byte addressable, and we can flip individual bytes if we want to in memory, but the most efficient way to access memory is with whole cache lines. So even though it's byte addressable, if you're going to do for highest read and write performance, you're going to step that up to reading or writing entire cache lines. Persistent memory is kind of in the middle. So the media itself has a very, very small native block size, and that's an ECC block. That's a regular server memory construct that we've just applied to persistent memory. And so you're not reading in 4K, you're not reading and writing in 4K blocks. The media itself is fundamentally reading and writing in 256 byte blocks. That's an ECC block. And how many cache lines is that? That's 4 cache lines. So this memory is addressable in a byte addressable way. You can flip individual bytes, but the most efficient way, just as with memory, the most efficient way to use it is in terms of a cache line. And then on the media, that cache line is going to be magnified out to an ECC block. The general latency is another place where persistent memory falls in the middle between DRAM and storage. So we're all used to storage being relatively slow, taking tens of microseconds to do something with a storage-based solution. And memory is extremely fast. It's at the other end of the scale, nanoseconds, 50, 60, 70 nanoseconds. Persistent memory is going to be in the middle. So its latency is not as fast as DRAM. And if anybody tells you that it's exactly the same as DRAM, they're probably upselling you to something else, I don't know. But in general, the latency of persistent memory is not as good as DRAM. And that's one of the most important things. So what that means is, generally speaking, if you take something that's really, really well optimized to run entirely in DRAM, and you run it on persistent memory, it's going to be slower, right? Now, it's not going to be in order of magnitude slower, but it will be slower. It will be slower enough that you will care about that difference from a design perspective. So again, just trying to reinforce the idea that this doesn't map exactly, that we're exposing an extra tier with this persistent memory. Another thing that I think is really exciting about this technology, which we're actually going to come back to this point later, but I want to bring it up now so I can reinforce it, is wear leveling and endurance. So I'm sure everybody knows that when it comes to using SSDs and NAND memory, this is one of the biggest limitations, right? NAND wears out, and it wears out relatively quickly. And so you need a lot of sophisticated wear leveling techniques to be moving your data around so that you don't exceed the endurance of the device. 3D cross-point memory and persistent memory in general does not have the wear leveling and endurance problems that we've come to know and love with SSDs. This is a fundamental part of how the media itself is constructed. And it is very, very different from NAND in this way. Or, yeah, from NAND. And then the last one here is cost. And as I said, we're not releasing cost and final cost and performance numbers right now. We're doing that closer to product launch. But in general, persistent memory is going to be cheaper than DRAM and more expensive than storage. So again, occupies a third tier that's in the middle between memory and storage. The main driver behind the rise of persistent memory is performance, as is probably obvious. But this slide kind of gives an idea of the journey that we've taken to get here and kind of what's at stake in this revolution. This persistent memory revolution that we're just getting to the point where there's a lot of these commercial products are starting to come out, but this has really been an over 10-year process to get to this point, not just by Intel, but by a number of companies that we've been working with and a number of independent efforts. And the left-hand side is where we started. So the left-hand side is a really good NAND SSD. So this is not a commodity SSD like you may have in your laptop. It's not a SATA SSD. This is an NVMe connected enterprise SSD. And you can see for all the investment in this technology, the media itself is still relatively slow. So the big blue bar here, to do a 4K read from a NAND SSD device, that's the amount of time you're going to spend in the media itself. And this is one of the reasons why SSD solutions today are already pretty well optimized. It doesn't really make sense to try to optimize your driver much more, or the operating system stack much more. That's all down here in the noise. Most of the time is spent in the media itself. The 3D crosspoint media and the persistent memory media is significantly faster in terms of how the media itself works. The switching frequency of the media is much, much higher than with NAND, much closer to DRAM. So that's what the middle bar represents there. So the middle bar is you've taken persistent memory and you're using it in an SSD form factor. And now the amount of time that's spent on the media goes down really dramatically, right? The time on the media goes down so dramatically that now the time in the operation stack, in the OS stack itself, in the driver, in the file system, in the kernel, are tremendously significant. So those are the new bottlenecks to remove. So by taking this persistent memory and delivering it alongside our banana in our DIMM form factor, we've done a bunch of things. We've removed the bus entirely. We don't have to go out over we don't have to talk to an NVMe device that's connected to the bus. That's a relatively long operation. We've removed the file system because we've bypassed it. We're going to talk about this more, but we've bypassed the file system. We've bypassed even the kernel. This is direct load store access to persistent media from your application with as many software layers in the middle as you want to have in the middle. But the far right-hand side of this, this is the potential for the kinds of performance that we can see out of this. Now, obviously, this is a little bit of an apples to oranges comparison if you can read the captions down here. But the two bars on the left are for 4K reads, because that's what SSD devices do. They work in 4K blocks. But as we saw on the last slide, persistent memory doesn't work in large blocks. It works in cache lines. It's byte addressable. So the far right-hand side, the latency bar there, is the read for a 64-bit cache line. And it is a little bit of apples to oranges, but that option was never available to us before. I mean, you can read a 64-bit cache line from a 4K block. You can treat a 4K block like it's byte addressable and just throw away the parts that you aren't addressing. We can do that. It just makes us terrible programmers. Nobody would do that in their right mind. But with persistent memory, actually treating things, actually touching your data structures directly, the way that you would touch them in DRAM, without assuming that you're paging them out through the kernel, through the page cache, through your file system. This, we think, is the programming model that holds the most promise. You can see at the far right, the little orange bar there is the read of a full 4K block, just to make a full apples-to-apples comparison. You can see it's still smaller than the fastest Intel Optane SSDs that we have now. All right, so in talking about programming for this stuff, there's a little bit of background I want to set here. The first is, as I already mentioned, this has been a huge process that's been going on for many, many years. One of the first things that happened was the formation of a new programming standard for this. So this is administered through SNIA. And pretty much everybody that you would have wanted to collaborate on persistent memory has been collaborating on this. I think Intel is in a pretty unique position to just the companies that we work with and the customers that we work with. We have a lot of opportunities to bring people together. And that's really what we've seen as our role in doing this, is to help bring this community together, because these changes that we're talking about are so fundamental they could never really be done in a strictly proprietary way. We're not just talking about changes to the hardware. We're not just talking about changes to BIOS and firmware. We're talking about changes to the operating systems. We're talking about new drivers. We're talking about new software stacks. We're talking about new ways of thinking about our applications. These are not things that you can just do quickly and easily. So standardization is an important part of this. I have the link here to the SNIA programming model. Please do check it out. And what you're going to find there is it's kind of refreshingly boring in a way. Because we've always had this capability to memory map files and move data around. And memory map files have been around for 25, 30 years now. Fairly old technique. And for people that aren't familiar with this technique, you may not have used it. But basically what we're doing with a memory map file is we're telling our operating system, treat this file as a region of memory. So I'm going to take a file that lives in storage down here, and I'm going to tell the kernel, do a mapping and bring that file into memory, and let's treat it as though it was memory resident. And that's what the cache in the middle represents. So the kernel's going to bring that file, bring that data into kernel cached memory, and then that memory will then be exposed up into the application's virtual address space. The application thinks this is just memory that I can manipulate. I'm going to flip this byte, I'm going to flip that byte, I'm going to flip that byte, right? And the operating system is going to turn around, it's going to take those changes, and then it's going to push those changes back out to the physical device in the 4K blocks that the physical device knows how to work with, right? So this technique has been around forever. Every operating system supports this. The reason why you may not have used this technique a lot in the past is because it's very inefficient, right? Because we're treating this 4K block device as though it were a byte addressable device. And that means that you've got this magnification now that when you're flipping bits or flipping bytes in your data structures, that's getting written back out as 4K blocks. So not very efficient, but a very good technique. So when the SNIA group first started to think about what's the general way to expose persistent memory in a way that operating systems will find it fairly easy to deal with, this seemed to be the best choice for doing that. Now, there's a lot of things in the SNIA programming model because it's designed to cover a bunch of different cases and a bunch of different scenarios and be very flexible. But I like this diagram as being one picture that brings it all together. What we have on the left is our traditional application stack, which you all know and love already. You have standard file APIs like the POSIX API. That's going to talk to a file system. File system's going to talk to a driver. The driver's going to talk to storage. And that's all a block-oriented protocol. And we're going to come back to this idea, but we kind of take our file systems and our drivers a little bit for granted nowadays. Most of what a driver actually does is things that we don't even think about at all, which is handling device-specific errors that come up, which are incredibly specific and hard to test and error-prone, to make a bad pun. But anyway, so we know that what's on the left-hand side here is very robust, and we've got a whole lot of years invested in making that good. And for persistent memory to try to beat that is a very tough bar to set. We've got 30 years of very, very smart people optimizing the stack on the left, and now we're saying, hey, let's disrupt it. And the only way that works is if you can deliver something that's significantly better. But we think that this is it. So as I said, when I first started, you'll see the bottom there says NVDIMM. It doesn't say persistent memory, and it doesn't say Intel. This is the SNIA programming model. You can take this programming model today. You can take an NVDIMM device from HPE, for example. These are already on the market. You can order one of these today. You can throw it in your server, and you can start programming with persistent memory. So NVDIMM is the generic term for persistent memory. Stepping up to the application, you can see that the first thing you're going to see from your application is if your application uses a standard file API, then you can continue to use a standard file API. What we're going to rely on is we're going to rely on a persistent memory aware file system to help with some of the optimizations there. The specific optimization that we're really looking for is to bypass the kernel's page cache. And there is a specific standard beyond SNIA for doing this. It's called DAX, D-A-X. It stands for Direct Access. And this is a very exciting standard. It originally came out of Linux. It was something that Intel helped broker with the different Linux vendors. And then we brought this to Microsoft. And originally, Microsoft, in kind of old Microsoft fashion, said, oh yeah, that looks really good. We'll take it, look at it, and we'll get back to you with what our version of it would look like. And then amazingly, after that, Microsoft came back and said, you know what? We're going to use the same API. We're going to use the same standard. It already exists. In fact, we're going to call it DAX. And it's amazing. It's amazing. So we actually have one standard for direct access that works across both Windows and Linux. And this is I think one of the biggest standardization benefits that really we've been able to broker in a long time. So the persistent memory aware file system, this DAX file system, that's the one that can do this magic. It's smart enough to know that I can skip the page cache and I can go direct. And it's really as simple as that. So whenever if you hear DAX, think skipping the page cache. And if you hear SNIA, just think memory map file, and you're pretty much off and running. So I mentioned DAX is already available on Windows. It's also already been integrated into XFS and EXT and the major Linux file systems as well. So that's our file system. So if we've got an application and it uses a standard file API, you can take that, you can run it on persistent memory. You don't have to change your application. Another thing I didn't mention earlier, but I'll mention it quickly now, is this persistent memory can be divided up. It can be partitioned. So we're typically not saying, I've got a DIMM and I'm going to give the whole DIMM to my application in a device way. Now you can do that. Certainly there's lots of databases that want to work with raw devices. You can do that. But what you're frequently going to do with persistent memory is you're going to carve it up. You're going to carve it up into different regions or different partitions. So on my NVDIMM here, my application's actually using both sides of this. So my application's using a standard file API, kind of in the center line here, and that's going to a region of persistent memory that is being exposed as a block device. So that's a legal thing to do, in fact, an encouraged thing to do, if that's the value proposition that you're looking for. And that's absolutely intentional, right? We want there to be easy ways to get started without having to make significant re-architectures to your software to get benefits out of that. So the standard file API and DAX allowing us to bypass the page cache has a lot of potential to improve applications without making any changes at all. The far right-hand side of this diagram is an application that has been evolved to take advantage of this load store access. And notice it could be the same application, right? This is an idea we'll come back to, but within the save application, I could say, yeah, I've got some standard file stuff, and I'm just going to use that, and then I'll have another part of my application. That's where I have an optimization opportunity. That's where I'll try out load store access for the first time. So we're still relying on the file system because it is memory mapped files, right? So we're still relying on the file system to do things like security checks, authentication checks, permissioning, things like that. But once that file is mapped, once we have those MMU mappings in place, that memory that's our persistent memory becomes part of the application's virtual address space. The application now has direct load store access to that media. So once this memory mapping is done, you have direct load store access. That means you're not going through the file system anymore. You're not going through the kernel. You have direct access to that media, and this is what gives you the fastest possible performance. One of the things that we have to do is we have to flush. So when we talk about persistent memory, let's not forget that there's a whole lot of CPU caches between us and our persistent media. And so this is one of the big challenges, is that you have to actually flush out to durable media. So we've got our L1, L2, L3, but we have to flush all the way down to the write pending controller and then down into the DIMM. So what does that mean? That means that the hardware is not providing transactional consistency, right? Which is just like all storage systems, right? If you're manipulating a data structure, you need to have transactions to protect against that. So just a few quick notes on adapting persistent memory, or adapting software persistent memory. The most important thing to get out of this talk today is that persistent memory is not exactly like DRAM. It's not exactly like SSD. It is a third tier. Think of it as a third tier. Think of it as combining this with the memory and storage you already have. Think about using this inside your existing architectures in a hybrid way, and you will be in a much better place than if you're thinking about, I'll just take everything I'm doing in DRAM or everything I'm doing in SSD and put it into this new medium. This memory is going to be used in different ways, but different applications. We already showed this. Some applications may use it in a file-oriented way. Some may use it in a load store-oriented way. Some applications may do both at the same time. There's also remote DMA capabilities. Persistent memory are, at least in the Intel implementation, is an RDMA target. So being able to remotely replicate directly to persistent memory is also a very interesting application pattern. The catch is that this exposes applications to some classic problems that before we could always count on the kernel or the file system to do on our behalf. In fact, we're so accustomed that we don't even really think about those problems because the kernel and the file system take care of them for us. So some interesting cases that we've tried. So we've been working really hard to look at different patterns, look at different strategies, do benchmarking, and see what are the different kinds of patterns that we'd recommend. And these are just a few, but you'll start to get a sense of the possibilities here. Wall acceleration is one of the most obvious ones. If you have a database or a queuing system that has a write-ahead log, taking that write-ahead log and putting that log on persistent memory. Persistent memory is very, very good at flushing irregularly shaped blocks of data, right? You're not going to have to write a whole 4K block. You're not going to have to marshal it into sequential append-only writes going out. Take your wall and let it do its thing. Now remember on the earlier slide we talked about wear leveling and endurance, right? So this is where that's really important. When SSDs first came out, one of the things that people wanted to do with their SSDs was say, hey, I've got this SSD and it's really fast and it's really great. So the best place I could put that in is I could use it for my transaction log, Because if I speed up my transaction log, I speed up the performance of the whole system, right? And what was the main thing that held people back in doing that? It was concerns over the endurance of the devices. And that's a real concern because you're saying, I'm just going to write the hell out of the device with my wall all the time. So that endurance factor when it comes to wall acceleration is really, really important. And I think this is a very important lesson to take away from the rise of SSDs. And thankfully, that's not, history is not repeating itself again. So the high endurance that persistent memory has is really important when you're talking about a write-ahead log kind of case. Persistent caches is another really, really great pattern for this. Everybody's used to caches, right? We don't have to talk about what that is, but one of the biggest problems with caches is refilling them. That can be a very long process, and you can have a lot of latency outliers when your cache is being filled that you wouldn't see in a normal steady state situation. But with persistent memory, you keep your cache in persistent memory. Now that's going to be a little bit slower than it would be if it was in DRAM, right? But you never have to reload it. So you get a very interesting trade-off there. For an in-memory database, it's kind of taking the cache idea to the next level. When you talk about an in-memory database like Redis, for example, what are the things that hold us back in terms of using it? The things that hold us back are we can't get enough DRAM in our system because we want bigger data sets than we have DRAM in our system. Persistent memory helps with that because the capacity of the memory is so much larger. It's also being done at lower cost, so you can actually afford to get that data into memory. It doesn't have any of the reloading that we talked about with persistent caching. So something like Redis, the first thing it has to do is stream all its data back from disk when it starts up. If you're talking about a Redis server that has terabytes of memory, that can take hours to reload that from SSDs. With persistent memory, you can bring up Redis, you can do a little consistency check if you want to, and you're off and running. Very, very powerful. The last two, hybrid and converged. Hybrid means that we're going to create data structures that live in multiple tiers. So maybe part of that will live in DRAM. Part of it will live in persistent memory. Then as that data cools, it'll be moved off to SSD or even spinning Rust. Again, opening up additional tiers. Converged compute and storage is bringing more data closer to the CPU so that we can do more with it, because you have that direct random access to your data. But as we said, there are some classic problems that come back, and the reason for that is that we're bypassing the kernel, we're bypassing the file system, and so the trade-off then is that there's more that the application is going to have to do to take care of that. So just some quick examples. Position independence. Every time you run your program, it's going to be in a different area of memory, right? But persistent memory doesn't change. So how do you deal with pointers that may point to a volatile structure, may point to a persistent structure, or even a volatile structure that has pointers to a persistent structure? That's a very tough problem to solve. Memory allocation and garbage collection. You can't just take your regular memory allocator and use it. It's not appropriate. And by the way, if you get a leak in persistent memory, how long does it stay leaked for? All time. It's not like you get a leak and then you just get to restart the system and then everything's great again. An errant pointer that goes wrong and does a bunch of stuff in persistent memory, it's bad. Transactions and locking. These are other options. The hardware is not going to protect against torn updates. You have control over flushes. You have control over when things get durable. That means you need some kind of transaction protection. If you grab a lock and your system dies, that lock doesn't automatically get reset because, again, it's persistent, right? These are inverted behaviors from what we're used to dealing with. Error detection and handling is maybe the biggest one, right? Most of what drivers do and a lot of what file systems do is hiding errors. And we as programmers are just not even really used to dealing with these kinds of errors. So the kinds of errors we're talking about here is not, oh, I got a bug, or oh, I did something wrong, or oh, I've got an off by one. The error that we're talking about here is that the media is actually damaged. There's actually poison on the media. There's corruption on the media. You're now loading that corruption directly into your virtual address space. There's no poison help for this, like you would get out of a normal driver and a normal file system. That's something that the application is going to have to deal with. So our call to action today, most important thing, consider persistent memory as its own tier. If you do that, that's going to get you on the road to thinking about this in the right way. Look for those breakout opportunities in your architecture to hybridize. Don't think, oh, I'm going to throw out the whole thing and start over. Look for the places where you can apply either existing file system APIs, or you've got something that you can use load store access in a limited way and get your feet wet and go forward. Intel is sponsoring a number of libraries that are related to this. SNIA says you can memory map this stuff, and your terabytes of memory start here, have fun, right? That's what SNIA is going to tell you. Intel's not the only group that's making libraries for this, but we think we have first mover advantage. Our library is called NVML. It's on GitHub. It's all friendly licensed. You can steal our code. You can use it however you want, even in your own projects. And the link here is on GitHub. We do all of our development on GitHub. This is all open source, and it's all developed in the open. We don't like get to a stable point and then release stuff. We're actually making all of our mistakes in the public eye. And the last one, you can start with this today. You can start with emulation. You can use DRAM as emulated persistent memory. You can try out these techniques, try out these ideas. But please, as you make your final design and tuning decisions, validate and tune on the real platform. Again, it's not just like DRAM. It's not just like SSD. So you can do a lot of prototyping, pretending that your DRAM is persistent memory. But in the end, you're going to want to validate those assumptions on real hardware. Thank you very much. Appreciate it.